Kæru gestir, ég heiti Sigurður Magnús Garðarsson og sviðsforseti verkfræði náttúruvísindasviðs og það mér sönn ánægja að bjóða ykkur velkomin á þessa innsetningarathöfn Birgirs Hrafnkelssonar. Innsetningarathöfnin í dag á sviði tölfræði, það fagsviðið hans Birgis. Þessar innsetningarathöfnir hjá okkur hafa núna nokkra ára sögu og tilgangur þessara athafna má segja kannski tvíþættur. Annars vegar þetta að samfagna Birgi með hans framgangi prófessor, sem alltaf tímamót á ferli akademísks starfsmanns og jafnframt viðurkenning á árangri hans á hans fagsviði. Þannig að það sérstaklega ánægjulegt að vera hér og samfagna þér í því, Birgir. Og svo hins vegar þá þýðir þetta það að háskólinn, sviðið og deildin telja að fræðasvið Birgis þá innan stærðfræðinnar sé mikilvægt þá fyrir íslenskt þjóðfélag, fyrir háskólann, fyrir okkar nemendur og fyrir í svona alþjóðlegu samhengi. Þetta einnig viðurkenning og ákveðin svona stefnumótandi ákvörðun sem tekin með þessari ákvörðun. Ég hef haft heiðursann að vinna svolítið með Birgi. Við höfum haft saman meistaranemendur og doktorsnemendur og við höfum líka reynt að birt greinar saman og ég vil nú segja það bara svona persónunótum að það sérstaklega ánægilegt að vinna Birgi, þannig að það mjög gleðilegt að standa hér og fá að kynna hann inn í þessa athöfn í dag. Og það mjög ánægilegt. Þannig að það mikill heiður, Birgir, að fá að bjóða þér hingað upp og halda þinn innsetningarfyrirlestur og eins og við sjáum þá titillinn hjá honum Physical Statistical Modeling Using the Bayesian Approach. Svo Birgir, gjörðu svo vel.
Takk fyrir Magnús, takk fyrir góða kynningu og takk fyrir að koma. Þetta svolítið ánægja að vera hérna í dag og ég var að taka stressið út svona nokkuð sjöfum síðan, tíminn sveiflast í samanni, en svona hægt og rólega þá byrjaði þetta að koma og ég ákvað að gera þetta á minn veg, við höfum svona rýmt til að gera þetta ákveðin hátt og ég ætla að byrja á íslensku. Það eru margir hérna inni sem við erum kannski ekki alveg endilega að vera átt þessum formúlum sem að koma á eftir og við erum til að tala á íslensku og segja ykkur svona frá hvaðan ég að koma og síðan ætla ég að vera með fyrirlestur á ensku og svona segja frá mínu og svona vera sýna upp á stóru myndina, en það koma nokkra formúlur, ég bara get ekki sleppt. Svona, var ekki betri hamar á hérna þetta? Jú. Hvað segir þið? Takk fyrir. Þetta svona titillinn á fyrirlestunum og þess að Sigurður kynnti. En ég ætla að byrja að segja ykkur svona frá því hvaðan ég kem og við setjum hérna mynd sem við tekin hérna á Íslandi og það kannski að því að það hefur alltaf verið svona sterk tenging hjá mig við náttúruna og það gerist frekar snemma. Þegar ég var strákur þá var ég sendur í sveit, ekki að því ég var óþekkur, en bara þangað var ég sendur til ömmu og afa og þar var ég á sumrin, mörg sumur, 2 mánuði eða meira, maður var alltaf úti og þarna var sjór, þarna var land, fuglar, bjarg og það sem að gerðist er að maður svona lærði bara náttúruna bara í hér og nú og ég fékk hana bara svona með sumardölinu og það verið mér mjög dýrmætt. Ég langar til að sýna ykkur þessa hérna mynd. Hérna sjáum við mig einhvers staðar á þetta myndi vera ég, 9 ára. Þetta Sigurður Hrafnkelsson frændi minn, hann hérna sjálfur. Þetta Þórður Jónsson, afi minn, og þetta Gísli, hann var vinnumaður. Og þarna verið að mæla sem sagt sjóinn, að taka sýni. Og þetta var gert á hverjum sunnudegi, hitastigið var margt og stundum voru tekin sýni. Og þetta fekk maður að taka þátt í. Þetta var rosalega merkilegt og spennandi. Og afi var líka veðurvaktunarmaður og þetta var sem sagt, þetta er 1970 eitthvað og þetta er svona okkur áratugir aftur í tíma og það var sem sagt símir sem var notaður hann var svona, löngstutt og þetta er svona síðan. Hann hringdi sem stundum veðrið og las upp ykkur ægilega talnarinn. Mér finnst þetta allt saman stórmerkilegt og hafði mjög gaman að þessu. Þetta hafði náttúrulega ákveðin áhrif á mig. Man har elst upp líka við þetta hérna bjarg, þetta látrabjarg. Það er stórfenglegt, það er kannski sum séða. Og þarna svo mikið í gangi, það líffræði, jarðfræði og sjórinn hamrar þarna á þessu. Maður svona öðlaði skilninga þessu hlutu með því að alast upp við. Og víkin sem að þau byggja þetta látravík er bara rétt hjá, það fjara, maður har ósjálfdan að sjónum. Og þá upplifum maður sjóum. Flóð og fjöru og stórstrengt og allt þetta. Og þetta síðast náttúrulega inn í mann. Og svo var maður alltaf úti. Hérna mynda kríu, það svo mikið að kríu hana. Og það sem maður spáir líka í henni er svona náttúrulega, það náttúrulega dýrin. Og hvaðan kemur krían? Á hverju lifa refirnir sem þeir gera. Svo eru rollur. Og amma voru með svona 120 rollur. Og þetta var svona samfélag búskapur og tók þátt í þessu. Og ég var alltaf að bíða eftir einu. Það var að kemur mórakt lamp. Þess að brúnta líka. Og ég beið. Það gerist aldrei. Ég held ég að svona átta mig svona þegar fyrir að skilja erfðafræði, af hverju það gerist ekki. Það var ekki móruður hrútur að það. Nú, ég mjög gaman á útivist. Hann búinn að pósa framhægt fossinn. Og ég var í skátunum og tók mér hjálparsveit og ég nokkrir félagar úr skátunum. Og við erum útivistarkallar. Hérna við hluta af hópnum. Hérna við með Björn Alfreðsson, Friðrik, þetta Jakob, Einar og Atli. Svo er hérna Egill, Guðbrandur og Halldór stattur í Noregi. Og Siggi Randið, þú varst með okkur skátan líka. Þannig að þetta er líka svona hluti af því hvaðan maður kemur. Það er útivistin og þá er maður í náttúrunni og það er bara, þá skynjar maður. Og Kobbi vinur minn, hann að stúdera outdoor education og útivist er mjög góð leið til þess að læra náttúruna og líka til þess að öðlast með sjálfsvist og svoleiðis. Og það er svona gaman átt að segja þessu. Við erum allir með hennar bakgrunn í þessum hópi og þetta er okkur mjög dýrmætt. Þarna erum við hjónaferð frá því í fyrra og það var hrikalega gaman hjá okkur. Og hérna er svona bara réttistæki. Þetta er bara eftir fyrsta bjór og það var mjög gaman hann í kvöldið. En svona, þetta er svona hluta upplæginu, en svo færist ég yfir í svona svo við talum svona hvernig ég færist inn í svona tölfræði og það sem ég núna, að þá hafi ég alltaf gaman af stærðfræði og samt náttúrulega náttúruvísindum. Það var alltaf þarna og svona pældi ég hreyfnisstærðfræði en hún var ekki fyrir mig, þannig að hafði á mitt áhuga á hagnýtisstærðfræði sem var ekki til hérna í Íslandi þá. En ég fór í vélaverkfræði og sá ekki eftir því, það fikk ég mjög góðan bakgrunn, það var 4 ára prógram. Svo fæ ég mig yfir í meistaranámi í tölfræði, tók ég mikið af tölfræði í meistaranámi í vélaverkfræði. Hluta til í Danmörku og svo hérna heima. Og svo var ágættur menn sem að leiðbindi mér, Ólafur Pétur Pálsson sem situr hérna og Guðmundur Jónsson. Og ég kannt þeim bestu þakkir fyrir frábæra leiðsögn. Og þeir voru með fyrirmyndir hvernig það var góða leiðbindi. En svo bara axla þetta þannig að tölfræðin var hérna búin að ná svona tökum á mér. Ég hafði mikinn áhuga bara að læra meira um þetta. Vissi svo hvert að þetta stefna, en þarna vildi ég fara. Og það sem svona verið með tóa í mig er þetta að geta nota stærðfræðina sem svona mjög struktúruð til þess að lýsa einhverju sem svolítið erfitt og óáþreifanlegt að einhverju leyti, sem þá náttúran eða einhver svona skipt fyrirbæri og geta einhvern veginn svona náð utan um þetta til að skilja það betur. Og það sem skemmtilegt í þessu með tölfræðina og þessi físíkina er að þetta þarf að koma saman. Það er alltaf mín skoðun. Vegna þess að við erum með mælingar og við erum með módel sem ófullkominn. Við þurfum að ná utan um þennan ófullkomleika sem er til staðar. Og ég myndi segja að það er það sem að það sem ég ætla að fjalla um í dag, sem sagt physical statistical modeling fjallar um einhver leyti, að geta náð utan um óvissuna. Hversu veit ég um þennan parametr? Hversu mikið veit ég um þessa stærð? Það er það sem við erum að sækjast eftir. Annað sem ég langaði til að minnast á að ég hef átt gott samstarf við menn eins og Sigur Magnús, Guðfinnu og Óla Pétur og Rúnar og nú var þetta Hessi bráðum og Þórhildur og það fullt af fólki sem eru að vinna með, Magnús, Páll, Karl, þið eru kollega mínir, nemendur fyrrum. Ég hef verið mjög lánsamur með samstarfsfólk og nemendur, bara að segja eitthvað. Sölvi, Helgi Gunnlaugur, Salme, Guðlaugur Salme og Sahar. I'm just saying that I've been very lucky with students, you being one of them. Þeir eru mörg inni, þannig að ég gaman að segja frá því og einhvern veginn hefur æxlast þannig kannski að það verið of fá í tölfræðinni að það verið þarna ég ekki glemt hér og Gíri Jónas Gjell líka, það var gaman að vera með þeir líka. Þetta búin að vera skal ég ykkur segja þeir líka, þeir eru bara allt Helgi og Bjarni ef ég gleymi einhverju þá bara því ég sé ekki og búin að vinna líka mitt með þeir kollega mínir, sitt bara í röðum. Ég er búin að vera mjög heppinn og það sem hefur gerst að því að tölfræðin er þörf svo víða og það hefur verið, ég hef beðið aðstoð hjá ýmsum aðilum og það hefur verið frábært og kyrst mikið af fólki gegnum það, en þetta svolítið skrautlegur listi í raun og veru. Og ég tók þetta saman áðan og ef ég man þetta svona næstuð rétt þá var ég í díkót og Hafró, það erfðafræði og fiskifræði, það svona sitt hvort, veðurfræði, vatnafræði og svo verkfræðigreinar ýmsar, störnfræði, vatnafræði, jarðskjálftafræði, matvælufræði, orkuverkfræði, svo jarðfræði, við varum að vinna nú með Páli og Magnúsi, og svo náttúrulega bara lífheilsan, ég var í lífheilsunum tíma, og það var læknardeildin og hjúkrunarfræðin og heilsuafræði, og þetta langur listi og það frábært, en nú ég fann afmarka með hans meira og ég held að það sé svona skynsamlegt, en þetta verið mjög góð reynsla, það mjög áhugavert að sjá hvernig aðrir vinna. En já, ég held að þetta svona dragi saman svolítið á hverju ég er komin hingað, á hverju ég er með þennan fyrirlestur og það einhvern veginn hefur bara ég held að svona einhvern veginn var mér ljóst að þetta var einhvern svo braut sem ég átti að taka, þannig ég bara farið á hana og þetta gengið vel, ég er mjög þakkláttur fyrir það. En er Látrabjargið, sem segir, það er magnað að koma þarna. Það sem ég ætla að gera núna, nú ætla ég að færa mig yfir í svona fyrirlesturinn og ég ætla að segja frá 6 verkefni sem svona nokkuð ný eða að fara af stað. Ég næ kannski ekki að segja frá 9 verkefnum, en það er alltaf aukkolleginn minn Marja Sigurður hjá okkur að ég komin í samstarf við HR, það er Marja Sigurður Guðjónsdóttir og Ágúst Valfels og góðu kollegar með verkefni jarðvarma og jarðvarmaverkfræði. Það er mjög spennandi að koma inn í þann hóp, glaður að vera boðinn í það og það er einmitt mikið af það sem þurfum að pæla í fysika-statistika-máli. Postdoc og doktorsnefn komin, þannig að það er alltaf að gerast það. Síðan er svona stjarneðlisfræði í kortunum með honum Guðlaug, þannig að það er svona framöndan. En núna er ég að sýna ykkur þá bara svona akkurat núna og ég ætla ekkert að spá mikið meira framtíðina. Þannig að nú ætla ég að skipta yfir í ensku og sýna ykkur þetta er yfirleitt yfir minn fyrirlestur. So this is an overview of my talk today, and first I'm going to introduce to you physical modeling and Bayesian hierarchical models. That's going to do a short primer on that. Then I will go through 6 examples where we have some physical phenomena that we want to describe and show you how we can model it with a Bayesian hierarchical model. Excuse me. These problems are, the first one is on glaciology. The next one is on flow in open channels. Then we have monthly precipitation. We have ground flows and intensities. And then I'm going to talk a little bit about computation, and that's when it becomes technical. So if you want to zone out, please zone out. But let's get started. So I've been taking part in a journal called Environmetrics. That's a journal, but Environmetrics is a large field. And in the words of Walt P. Gorse, he's editor-in-chief of Environmetrics, it's the application of mathematical and statistical methods and theories to the analysis of data in the environmental sciences. So it's about using mathematics and models, mathematical models, using statistical methods and theories in this field to analyze data that come from the environment. And this is obviously very wide. This applies to many fields. And my faith is that this is a growing field. We have biometrics. Some of you know biometrics. That's a huge field. I think this field will grow quite much in the next decade because of its importance. We're just in the news, we're hearing all kinds of things about the environment. We need more data, we need more models, we need more research. So I'm looking forward for the future. A little bit on physical statistical modeling. In short, it's about applying the laws of physics or using output from physical models within a statistical model. So we can get the physics in. And then also, when we are constructing our model, it's about combining information based on knowledge of physics and information found in previous data. And what I'm talking about here is that when things are a little bit more fuzzy, we can use data to kind of just get the scale of things. When we don't have kind of a single simple law, like gravity, we know how that behaves. The thing will fall down at a certain rate. But I'm talking about when we have things that are that we have some data, we have some knowledge, and we want to put it all together. These are the works of Mark Berliner from 2003, and he wrote 2 fundamental papers on physical statistical modeling. This is in a journal of geophysical research, and that's one field where you apply these models. Basically, what he's saying here, I'm not going to read it out, that we have 2 important laws. We have Newton's second law, and we also have Bayes' theorem. And Bayes' theorem can help us put probability on things we don't know. And putting these together is very helpful. That's basically what he's saying. And he says, this separation is absolutely surprising. And I think we realized after that, this is a few years ago, that this is very true. We should be fusing data and models together. The Bayesian approach, it's a statistical method, and it's very useful for modeling uncertainty at all levels, meaning that there's some uncertainty in the data. The models that we have are imperfect, so there's uncertainty there, and there may be some other uncertainty. And we can assess the uncertainty of parameters. So we know a little bit, okay, how well did I estimate this parameter? Do I know something, or is it really vague? And we can also predict unobserved quantities. This is all very useful. And the Bayesian approach requires at least 2 things. You need a prior density, and that's basically explaining to you and others how much do you know about this quantity. And you also need density of the observed data. To give you a simple example, let's think of a dice, and you want to figure out how often the number 6 is coming up. And we would expect it's going to be 1/6. That's kind of what we expect. But if we suspect that it might be a fizzy dice, then we can put a density like this on this line here. This is from 0 to 1. This is explaining to us, this is showing us what our prior beliefs are about these parameters. It's very likely here, but maybe this is a very strange size, and it might be close to 0, and it might be even, there's likelihood of it being 0.5. So we are kind of open about it, what the true probability of getting 6 is. And when I say the true probability, I'm thinking about, I'm actually thinking about it in the frequency sense. If you throw the dice again and again and again and again and again, what will the proportion of times that you get 6? Well, I think this is reasonable. If we throw the dice 40 times and we got 6 11 times out of 40, our beliefs about this parameter have now been changed. And we are more certain about the value. It's probably between 0.1 and 0.3 as opposed to 0.05 and 0.04. So the posterior, this is the prior density, this is the posterior density. It's showing us how much we know about the parameter after we got the data. So this is explaining the kind of basics of this way of thinking. And again, in the from Berliner, both 96 and 2003. When we have a little bit more complex model than just a dice, then this is a general setup that we can rely on. It's a 3-layer level, or a 3-layer model. We call the first one a data level, the second level is called the latent level, and then we call it parameter level. And the first level, the data level, is basically about saying, if I know the physical parameters, what's the distribution of the data? So condition on, I'm assuming that I know something about the system, but what's the process generating the data? And this is often where measurement error comes in. So we don't measure it exactly, then we can put that uncertainty in at the first level. The process level is conditioned on the parameters, and the process level contains the quantities in the physical model. Could be temperature, it could be or mean temperature, while the data would be observations of temperature or precipitation, for example, or some other important parameters. And we will have a whole bunch of parameters that correspond to the process, but we also have parameters that are kind of key parameters. A few key parameters that are kind of specified at this level, the parameter level, and that's where we assign a prior distribution to these parameters. I hope this will become clear to you as we move along, but we have this 3-layer setup. What's great about this is that we combine two sources, data sources and size. And variability is taken into account at each level. So this is a nice setup. We put it in a mathematical frame, then we can set it up like this. Y is the data, and we condition, so this little bar here means we condition on x and theta, and we assign this density. We condition in the second level, we say something about x, condition on theta, assign this density, and then for theta we assign a prior density. And just a little input, if this density here is Gaussian, then we have a latent Gaussian models, and these are used a lot. Okay, so this is a little bit technical, but just it's really the same, just framed in a mathematical format. Right, and this is Bayes' theorem. How do we learn about parameters? X and theta are unknown. We have the data, so the data is known. How do we learn about these parameters? We use this theorem, and so C is a constant, and we just have to multiply all these densities together. So we really have specified everything when we were here. Prior, this is the latent level, the data level, and we can start working on it. So the nice thing is that we don't have to know C, and there are now methods that can handle this without knowing C, and that's really important. C can be hard to compute in general, so we just so we usually just think about it in this manner. And this density here is called the posterior density. And that's where we get from the posterior density we learn about how much do we know about the unknown parameters after having the data. So we start out with knowing something, but once we get the data, the prior posterior density is going to be much narrower in most cases. Hopefully you will see some examples, or hopefully examples will explain this a little bit further. Yet another important thing are Gaussian processes. And here is an example of a Gaussian process in 2 dimensions. These are extremely flexible functions and extremely useful because think about it this way. We can write function using x squared, x to the third, and so on. These functions just can stretch and bend in various ways. But there are some restrictions. We can assign them to be continuous in general. We can assign the second derivative to be continuous in a certain sense, and also the first and second derivative. So we can assign certain behaviors. But having a function like this, we are in a much better position to model something that is changing in 2-dimensional space. We don't know everything about it, so the data will help us learn about the shape. So that's just a short version of that. Let's get started with the first application, and this is about glaciers and glaciology, and I'm very proud of this project. I met Guðfinna Algeirsdóttir, she's sitting here in the room, and we started talking. and we saw an opportunity to apply for Aranish support, grant at Aranish, and that worked very well. So we have, in this group here, we have Birgir Hrafnkelsson, he's here in the room. And Guðfinna Pálsson, he's been working on glaciers for decades. Alex is also here at the university. Birgir Hrafnkelsson is involved in this project. And then we have a postdoc here, Christopher Whipple and Paul Ruhr. These are, let's say that these are very fine statisticians that I was fortunate to get on the team. So they are collaborating with us. And Giri already met Chris Whipple. And Håvard Ruhr, he's Norwegian, as the name suggests, but he is at Kaust, and that's in Saudi Arabia. So what we want to do here is to model Langjökull Glacier. What I'm showing you here are figures that we got from the glaciology group here at the University of Iceland. This is showing the track that the scientists go when they measure the glacier. So they measure at certain locations, and they are measuring how much ice was coming that year. They go actually twice a year and collect data to know about the accumulation. Here is a figure, basically it's an estimate of the surface here. How high is the glacier at this particular point? So this is where we are going. Giri has been working on this for 1 year. We are still proving certain concepts. So we are working on the methods, but we actually got a really good idea, and I think it came from the glaciologist. We have a method, we want to test it, but it's hard to test it only on the data. So they found a paper where they have the exact solution. That's exactly what we want. So we have the exact solution for the surface. So then we can simulate from that model, and then we can test if the method is going to capture the truth. And so far, so good. Once we have established that, we're actually far in, then we can go for the data. That's going to be the next step of that particular project. We were fortunate enough to go to Vatnajökull. So this is Giri Gopalan. He is from the US. This is myself, and we think we are so cool. So this is on Vatnajökull. We didn't go to Langjökull, but this is Vatnajökull. And this is what you see in the background is Grímsvötn. This is an awesome place. Maybe some of you guys have been there. And we participated in the measurement process. And that was a lot of fun. This is Finnur. He's been on the case for, is it 30 years or more? Yeah. Yeah, he knows a lot. And he really enjoys being there. You could definitely tell. And this is his wife. So yeah, we got into it. So Giri is working on the drill. And yeah, so we have some electricity here and just drill down. And we collect the ice. It's put on this little thing here. And it's basically measured, how long is it, and also how heavy it is, isn't it? So that's an important factor. So then you get an information about where you're at, and we drill as far as the ice for that particular year to go down quite far. I think it was 6 meters, 7 meters this time. So the stick was getting longer and longer. And we're gonna put it down here and just drill. This was actually a lot of fun. I'm taking a go at it here. Finnur's trying to calm me down. But you have to notice that this guy here, this is Gunni. He's wearing a standard equipment. It's called puffin pads. It's really important to wear these. And this is Grímsvötn. And it's magnificent to be at this place. I really enjoyed it. So this was actually just this summer. So let's get into the modeling. We have the data level, and at this level we're collecting data on the mass collapse. How much is coming over the winter? How much is kind of basically vanishing over the summer? We have surface elevation to some extent, and also bedrock measurement. So this is the data that we have. At the lake level, we are currently using a so-called shallow ice approximation. and we're testing it on a test case. But what we have to do is to add a Gaussian process to model the error in the model. So the model that we have is shallow ice approximation. Even though it's the right model, just because of numerical errors, we have to do it on a grid, we get some error. And the Gaussian process should pick it up. That's what we expect to do. Then we have important physical parameters, the basal track, what's the resistance at the base. And then we have viscosity, which is the kind of how the resistance in the ice itself. And so this is a simulation. So this is a computerized glacier, put it that way. So we have 2 time points here. This is the exact solution, and then it's in 2 dimensions. And we also have time as well. And we can see there's a slight change in time. And the simulation is about kind of computing at several time steps. You see how it changes. But then we assume that we collect the data in a similar way we do at Langjökull. We have just a few sites to pick up what's happening here, and we want to recover this. This is the truth. In reality, we don't see this, but in this simulation we can. We simulate data with some uncertainty, and we want to recapture the truth. And the line here is basically saying, okay, this is the viscosity. That parameter is recaptured because this is the true value, and this is the posterior density around it. So it's really graphical, and that's really good. And this is a cross-section of the glacier for a particular time point. And so we have the truth, we have the estimate, and the bounds around it are the posterior kind of 95% interval. So this is really good. It's actually graphing what it should be graphing. So these results are promising. So this is the test example. We will go into the actual thing sooner than later. And these are just certain estimates of the thickness at a few points. So you can see that it's capturing what it should be capturing, basically in most cases. And it's right. So we think we're on the right track here. Okay, yet another one. This is discharge rating curves. I've been working on this for a very long time. And what I want to show you is the work of Sigurður Magnús Garðarsson, myself, and Helgi Sigurðarson. He's a former master's student at the university. But there have been other people that have come to this problem. And 2 of them are sitting right here in front of me, Helgi and Sölvi. And people from the Met office have been working on it. At least 2 master's students, Kristinn Ingimundarson, Snorri Árnason, and also Árni Snorrason. He is the chief at the Met office. And then we have Odin and Njáll as well. We have also other people. Axel, he was working closely with Sölvi 2 summers ago, and Halla was working with Helgi. So this is ongoing, and I really want to show you this because it's so close to us. It's about our rivers. We have flow in the rivers. We can measure the height of a given river. We can see what's the water level. How high is it? There's a great indicator, and it's easy to estimate, or actually to measure. We can capture it with equipment, and it's actually digital, so you can observe it every minute, 10 minutes, what have you. Just have to collect the data. But then on the other hand, we have the discharge itself, and this discharge is actually computed based on the previous time series. But this is probably very close to the truth. So this is how much water is flowing in this period here, 2014, 2015. And knowing about our rivers is important for all our hydroelectricity power plants, that's for sure. So having a method to basically go back and forth, meaning that you got the water level, how do you project it to discharge? How do you do this? You collect data in pairs. So you have data on the water level, you're subtracting a constant here. So at 0, if this is 0, then we should have 0 discharge. We collect the pairs, and we can see how much is flowing. So you can see this relationship here. If you take log on both scales, both for this one and that one, you get a linear relationship. most of the time. And this is where this became interesting, because sometimes you don't. So the log relationship is not linear. There's a bending down here and there's a bending up there. So the linear model doesn't apply. And then you start wondering, why doesn't it apply? Shouldn't it always work? If you look at this relationship, the linear relationship, then it's just empirical. So why should it work? It works sometimes very well, but sometimes it just doesn't. So we kind of decided to look under the hood and see what's behind it. What I want to show you first is that Sölvi and Axel created this wonderful app 2 years ago, and it's now being used at Veðurstofa to kind of as an aid. And sooner than later we'll have to go public. So it's available. I want to show you this Shania. So the methods that we have developed, and now you can basically log in here and download your data set, and it will produce the curves you want. Of course, there has to be a nice picture here. And if you go to this web page, you can hear Sölvi explaining how to do. Teaching video. So yeah, this is great. I'm very happy with this app. So as I said earlier, we can think of a relationship like this. This is an empirical relationship. If you take a log on both sides, it becomes linear. So we have this constant and this constant, these are unknown, times this variable here. It's linear because we have slash here, constant times something that we know. Kind of more or less. We don't know C perfectly, but it's linear. And this works in many cases, but not always. So the main factors that we have to worry about here are indeed the physics. And I'll show you here a cross section. So think about a river that is looking like this for a very long stretch. That's the kind of hypothetical model. And so there's some slope that kind of pulls the water down. So that's the gravity coming in. But then you have the perimeter here. That's the part of the water that touches the river base all the way up here. That's the thick black line. This is kind of top of the water. And then you get resistance. So it's basically weighing kind of the gravity versus the resistance, just as the water is flowing on the riverbank. So it's friction versus gravity. And this is this physical law here is not new. It's actually quite old. But what it's about is that we have the slope here that has to do with the gravity. We have some constant here, and this is a ratio between the cross-section area and the perimeter. So the area is just the area of the cross-section, and then we have the perimeter down here. So this is a key factor. It's a geometric factor. We also have Manning. It's a very similar formula that he's using 2 over 3. Its formula is slightly different, but it's really more or less the same. And then you can rewrite it like this. So we have P here, we have A here, this is the area, this is the perimeter, we have X floating around, and this is some parameter. And this parameter has to do with both the slope and the friction. Okay. So the trick here is to say, let's use this physical law in our modeling. And we start out with a physical model that is like this. It's Q as a function of h, that's the water level. And instead of having b in the exponent, we put f(h). And then we say this should be equal to the physical model. This is the statistical model. This is the physical model. And let's see what happens. And if we do this, we can say something about f. It's a function of a and p. And a, capital A, and then little a is the discharge at water level 1, for example, 1 meter. And this is really helpful because now we have a handle on things to some extent. For example, this is a simulated example. If this is the cross section, looking like this, then this is what f of h will look like. And I could simulate more of these, kind of guessing how the riverbank looks like. And then I can get information about what this should be in terms of values. And that's valuable, because then I can put a prior on that function and use it in my statistical model. So that's how I'm putting the physics in, and it's based on a physical law. If we take some regular forms, this is a rectangle parabola, this is a V-shaped cross-section, and then this is kind of inverse parabola. If you look at these, what happens to this function f? You can see that it's actually constant here. This is a special case. So for the V-shaped one, it's constant. That's good to know, but it's only for this one. And the V-shaped one is just a single one out of so many. So for the rectangular, it's even changed in this water level. It's going from approximately 1, actually starting around 0.7, and then it goes down. For the parabola, it's actually very close to 2, but this still varies a little bit. And for this one, we get very large values. But this is not a typical natural cross-section, but this is very useful to have. So the statistical model should involve this in particular. So instead of B in red, we put F here. And now we have a model. We just have to add an error curve here. And we model this function here with a stochastic process. It's basically a constant stochastic process that can do a little trick for us. But it has to be continuous though. And this is working quite nicely, because if you apply the usual model, we're going to be off. It's going to be way off here. If you apply this model, we can see it has the ability to stretch and bend, and it will capture the data much, much better. And if we do it on a log scale, you can see that the linear relationship here, even though the bounds are tight, this is a prediction interval, then you can see it's bending here, and it goes slightly off, and it goes slightly off here as well. And you can see the little bending here. The points are very narrow here, and this is a better model. We tested that using statistical methods. And this is a residual plot, and here we can see it also very clearly. So this is a very promising model, and we are actually looking at, and we have a few results from Helga and Halla, that what if we know the cross-section? Can we get some information about the cross-section and estimate that, and then we put it in the model again? So this is without seeing the cross-section, but if we know a little bit about it, is that useful information? And that needs to be taken further. And so far, what we have seen, it looks promising. And this is the exponent. You can see it's the bounds are actually wide, but there's a change here. It goes from 2.5 to 2. But the main thing is that it does capture the data a little bit better. Okay, the next one. Modeling of multiple precipitation. This is based on a master's thesis by Atli Norman Sigurðsson, and we had a good collaborator in Philip Crochet. He was at the Metafis. He provided a lot of data for us and was involved. So basically what we want to do is to take data on precipitation, monthly precipitation. We don't have that many sites. However, we want to predict at a very fine grid. How can we do that? We need a physical model that tells us approximately what's happening at the grid points, and then we correct it using the data. So with only 40 sites, we don't have a whole lot, but it should be enough to give us the right idea. So these are the sites that we have. So we observed data from these sites. And this was over 50-something years. These are time series from January and July of 4 particular sites. This is Kvískepp. That's a heavy-duty place in terms of rain. And you can see that January is actually, we have the same scale, so January is really, really heavy. This is box plot of the results. What you can see in this figure here is that this line here is the median. This bar here tells us about the variability at each site. And what we are seeing is that both the median and this variability are not constant in space. So this is kind of going counterclockwise over the country. Here, this is the eastern part. We have Reykjavík here, and so on. This is the northern part, and when you get to the eastern part, it goes up. So there's a very strong spatial signal here, and the variability is also changing. So we need to capture the median and the variability. And that's exactly what we did. And so here's a formula, just to help out. This is alpha is where the physical model comes in. I'll show you that in a little bit. This is a temporal factor. Each year is slightly different. We have to take that into account. This is the difference kind of within the country for that particular year. This is measurement error. So we fuse it all together. Right, this is where it comes in. So this is the covariate, the meteorological covariate. It's on a 1 by 1 kilometer grid. This is a single parameter called beta, and this is a stochastic process in 2 dimension that kind of will fix what's need to be fixed. This should be close to 1 if this is a good covariate. And let's see what happens in a little bit. We do the same for the scale, and we look at log scale. We set up the same model. This is from the meteorological model. This is a single constant. It should be close to 1. And this is a correction, spatial correction. And the results are such that for the first one, for the median, we get 1.06. That's fairly close, but you're a little bit further off here. And also in this model, the spatial model is picking up much more. The model is really good for the median, but not so good for the variability. And so this is the covariate for the median. And then if we use that to predict, we almost get the same figure. It's just tilted up just a little bit, by 6% approximately. And you can see the hotspots here. This is the Kvísker, and you can see the glaciers over here, and the southeastern part. This is the covariate for tau, the variability. It looks like this, but you see that the prediction is slightly different. It's not only tilted, but it has to kind of adjust. It's adjusted in the right places. Maybe you can see which one. I guess maybe it's in the in the western fjord. So the variability was underestimated there. But this is all very useful. Why bother do this? What we have here could be used in another model for ecology or for agriculture and so on. So these can be kind of then what we have here. Now we have better faith in our predictions, and then we can take it and plug it into another model. That's where it comes in handy. Okay, next one. The ground motion intensities. So this is work with Sahar. She's a student here at the University of Iceland. She's coming all the way from Iran. We've been working, she's under the direction of Benedikt Halldórsson. He could not be here, unfortunately. And this is based on a project that he and his colleagues got Iranian support for. And it's basically about modeling seismic risk, and it's about earthquake fault monitoring. And what is being used here are these dense arrays that help us measure ground movement. So there's a array in Hveragerði, and there's one in Húsavík. Yes, exactly. And this has been a really interesting project. Many people involved. The interesting thing is that the model that is applied here is so similar to the model that I showed you before. And that's this nice transfer of statistical modeling. It is just take it over there, and it was more or less the same. That was pretty nice. Let me show you what this is about. Okay, sorry. There are two other students, Milad Kovsari and Tim Soneman. They've been working on similar projects. They're also PhD students here. And we have Russell Green from Virginia Tech. But there are also other participants. This is kind of more on this particular part of it. So here we have a figure of, this is basically Hveragerði. So here we have the South Atlantic seismic zone, this thing here. This is the area of Hveragerði, which is here, of course. What we see here is activity around Hveragerði. A lot of activity, definitely. Selfoss is over here, Hveragerði is over there. And in the top figure, you can see, I think it's about 12 stations rather than 10. And this is the array. So there's measurement equipment at these particular points, and they measure all movement that can be observed. And most of it is kind of small scale, isn't that right?
These are aftershocks from the main shock, which is indicated by the star in 2008 August earthquake, and we recorded more than 1,700 aftershocks after the main shock during the year of activity.
Right, 700. 1,700. Right, that's a whole bunch. And then you were able to use most of or part of them at least in our analysis.
We somehow published the data, and we are using for this particular projects more than around 700
right.
aftershocks.
Right. So basically we have 700 observations, and each observation involves a single measurement for each site.
Yeah.
Right.
Three components. Yeah.
Right. So we have vector observations, and the ground motion intensity we're looking at is peak ground
Peak
acceleration. Right.
PGA.
Right. Exactly. Thank you, sir. So this is the great thing. You know, you don't have to be an expert on everything. You rely on good people around you, and that's how things get done. You can't do everything. It's possible. Impossible. So what we have here, this is showing the geology around Pirrakeli. Even though this is only kind of 2 kilometers wide, maybe 2.5, then it's not homogeneous. There's a lot of variability in the geology. And previously, scientists and earthquake engineers have assumed that this would be just homogeneous because it's so close. But one of the things we wanted to prove is that even though the stations are close, there will be a slight difference because of different geology. So this is a geology map. So we're going to tease out the side effect of each one. And the side effect is right here. It's hidden in alpha S. We have other factors. This is basically the effect of each earthquake. We have an additional measurement error, and this is additional spatial signal that we need to take into account. But let's focus on the spatial effect. This model is identical to the model that I showed you just seconds ago. And the observations are log 10 observations of peak ground acceleration. That's used quite frequently. But this could be applied to any ground motion intensity. The first term takes into account the magnitude, the hypocentral distance, and then that to the origin of the earthquake. So we have a simple model picking up the main things in there, but still we need an even term, and we also need a side term. So this is capturing kind of the big picture, but not all of it, certainly. And what we have here is that this is the spatial signal, and to indicate kind of the change, we've predicted between the points, and you can see that this is on log scale, so this basically means that this is kind of minus 50%, and this is plus 50%. So there's a substantial difference between the sites. Kind of either lifted up or down. After taking everything else into account. So this is the side effect that is left. So this is an important result. Wouldn't you agree, Sahar?
Sure.
Thank you. Okay, so, and this is the event effect. So there's also great variability in there. So that has to be taken into account as well. Okay. Right, and this is ongoing. You guys have so much data. It's an endless source. That's really great. Okay, it's great that most of you are awake now. Now I want to kind of go under the hood. And this is part of Ole Birgir's thesis. He did a great job 2 years ago. He worked on it for a few years.
Very long time.
I don't know, 5 years maybe? Yeah, that's usual, without the masters. But he did a great job, and what we have here is a computational method, because often when you set up these models, you run into a wall, because how do I compute? There's a lot of software out there, but it's currently being developed. And we were in close connection with people in Norway at NTNU, and they have developed a really nice method called INLA, and they can compute for certain models really fast, using great approximations. But for this problem, we couldn't. So we ran into a wall. So what Ole did was to look at what they had done and extend it. And he was successful, and I'm going to show you what happened. Helgi Sigurðsson, he was a master student here. He was participating, and then we had Daniel Simpson at the University of Bath. He was involved as well. So basically this is similar to the precipitation problem, the monthly precipitation, but now we're looking at annual maximum precipitation. That's an important quantity for design, and I know that Jonas Eliasson, I think I saw him here, he has been working on this for a long time, and this is used in design. So it's important to have these estimates right and sensible. We use the same source of information, we use this methodological model, and we are able to predict quantiles. This is the 20-year event for precipitation. That is what would happen kind of on average every 20 years, approximately. So here we can see what this looks like. This is similar to the previous picture. But we had some complications that we had to take care of. So this is the result. So at least you know what I'm talking about. But now I want to show you what's behind, what we had to do. So I mentioned this latent Gaussian model, and that's what our colleagues in Norway developed. They developed a computation method for that model. But that approach had limitation. They were only looking at it for a single parameter, like the location parameter or the mean. And then all the parameters were kind of fixed and non-spatial. We had to worry about 2, and in a few cases 3 parameters. And that made things different. We couldn't use the software, and we had to crank through it ourselves, mainly Olapad. So this is the LGM. And I showed you something similar to this. We model the data. We model here with a normal distribution. And then we have the hyperparameters floating around. And this is what we want to approach. And this is actually useful. This assumption here, normal assumption, is useful as we can help in terms of computation. So let's think about a density where you're interested in location and scale. And we want to model both of them spatially, not only the location. So this is the location parameter. These are covariates. These are the typical parameters in the model. This is a spacing effect. This is an error curve. We do the same for tau. We have covariates, and then we have a spacing effect. So we need to tackle this together. We assign priors to all the parameters, and we have to kind of combine everything up again. We're going to reconnect everything. So we put mu and tau in the same matrix. We put all the parameters in mu, so we have eta and nu, and then we create new matrices so that we can write it in a more simple way. And this is, now we can write it in this form here. It's simply eta equal to c mu plus epsilon. Given that, we have the prior density written up in a nice way. And what is nice about this is that this is the inverse of the matrix. This is the inverse of the covariance matrix. These matrices are sparse. They have very many. Most of the elements are 0, and that's really important for computation because this matrix can be used directly. So it is denoted by the inverse. We make use of the fact that the data density only depends on eta. We set up a sampler that is basically based on breaking it up. So we sample first nu and theta from this density here. This is a conditional density based on the posterior. We sample eta, then we condition on nu and theta. So this is a standard setup, but we are making use of the normal assumption in both cases, or use of the normal distribution, let's put it that way. For example, nu conditional on y, eta, and theta is a normal density. The conditional distribution, we have the form here, and this is a sparse matrix, and we make use of that. And then we sample, for that step, we first sample theta, and then we sample eta. We have to compute this ratio here. That also takes some, there are some tricks needed to help with that. For the parameters at the data rich parameter, the parameters that show up at the data level, we approximate it with a normal density and propose values using the normal density, and then we test the values. I'm going very quickly through this just to give you the big picture. There are many formulas here, as I warned you about. Just to show you the results, these are kind of diagnostic plots for the sampler. We want the blue curve to go into the red line, or in the green zone, sorry, and it does. So that's a good indicator. And also, this is autocorrelation plot. If this plot is decaying fairly quickly, that's a good indicator. This is really good. This is quite good. So we're very happy with the results, and it works for this setup. So for any model of this sort, this can be applied. Round 2, using what we learned from this project, I'm into another project with Árni Jónsson. He's sitting here as well. And we have collaborators, Håkon Bakka. He's also from Norway, in Saudi Arabia. And that's not a coincidence. He's a student of Håvard Roa that we saw earlier. And this is Ilaria Prosper-Sini. She's at the University of Bath, just like Ben Simpson. So we've been working with these. Håkon is helping us with the computation. We're actually using England to help out. And Ilaria is helping with the data. So the data that we have is it's from UK, and oops, uh-oh, I lost England, sorry. Let's go back. Oh boy.
It's Brexit, man.
Yeah. Just want to show you real quick what we have. Okay, this should be sufficient. Right here. Okay, this is UK. You can see it. I want to show you. This is a web page where they have data from all these sites. More than 900 sites. This is Northern Ireland included. And Ilaria provided us with flood data from all these sites. It's a really big data set, and it has been tested and used quite a lot. And it's a great test. If we can apply our methods to this data, then we're in really good shape. But we're kind of halfway through. And what we want to do is, one of the things we do are spatial predictions. And just to keep it simple, I'll show you very briefly the model. We use the generalized extreme value distribution. We compute the maximum likelihood estimates, and we use them as our data. Because given these, and also the Hessian matrix, then we have most of the information in the likelihood. So we don't have to use all the data. We count on these estimates here, that they inform about what we need to learn about. We plug this into the appropriate vectors. This is actually the same data that we showed up before. So we're using the same structure here. And basically, where we're at is to model eta hat as data with a normal distribution. That's the trick here. And it seems to be working fine. But we have to wrap up a few things. But Árni is halfway through. And here we have linear predictors for 3 parameters. And preliminary results are based on this triangulated grid. So we're using a spatial method that relies on a grid like this, giving us a Gaussian process. And so these are predictions for the location parameter on a log scale. And there's a very strong and clear spatial signal that has to be taken into account. And you can see that kind of the sites here that are nearby, they share the same kind of ups and downs. Blue is kind of down and this is up. And you can see that on this scale, this is a very strong signal. No doubt about that. And then we can say something about the uncertainty. And what you see here, blue means low uncertainty, yellow means, and red is higher. And you can see that it's related to the points. If there are no points nearby, you get more uncertainty. And that makes perfect sense. So if you have many sites in one location, you can easily predict between them. If they're further apart, you get more variability, uncertainty. This is the location parameter, actually scaled on a log. It's on a log scale and also scaled with the mean. Strong signal here. And this is uncertainty. And yeah, this is where we're at. And we're going to wrap it up this winter, hopefully. So basically, what I've showed you in a few examples is that the Bayesian hierarchical model is a very flexible model, and it gives us interpretable results for physical statistical modeling. And we looked at 6 applications to give you a feel for what can be done. And that is actually what I want to say today. So thank you very much.
So thank you, Birgir. Do you want to entertain 1 or 2 questions?
Fine. Sure.
Is there 1 or 2 questions that are burning to come out? All your students know your material, I guess.
Yes, sure.
Okay, so thank you very much, Birgir. It's a pleasure to see how far and wide you have gone, and you gave a very good overview of that. So thank you very much for that. The school wants to give you something to. So let's go to the middle here. So something to so we can keep this here somewhere. So this is a book. This is the thesis, Untitled Chapter, Birgir Hrafnkelsson. So congratulations. Thank you. And so with that, I just would like to, I'm going to switch over to Icelandic. Mér langar til að þakka ykkur kærlega fyrir komuna, gaman að sjá hvað margir eru hérna í dag og að sjá Birgir í þessum tímamótum. Og það eru smá veitingar frammi sem ég bið ykkur að njóta og þar getið þið spurt Birgir út í jöfnu númer 7 held ég. Takk fyrir í dag.